Okay, great. Thank you very much for being here. The topic for today's talk is enumerative geometry and modularity in two-modulus K3-fibered Calabi-Yau threefolds. This is joint work with Boris, Pioline, and Thorsten Schimannek. Boris is a string theorist. Thorsten is a half-string theorist, half-mathematician based in Utrecht these days. And this is based on our paper we posted this summer, which incidentally is a HEPF posting, very appropriate for the mathematical physics theme of this workshop. But today's talk will almost entirely focus on the algebraic geometry aspects of this work. Oh, okay. Yeah, good. So some motivations. So one motivation is to find new Calabi-Yau threefolds. Now, new can be measured in various ways. Usually we say new in the sense of new Hodge numbers, something topologically distinct from any we found before, but also new constructions and better representations, more useful, more informative, more complete in the sense of moduli problems, representations of old realizations of Calabi-Yaus. And then also to understand the modular properties of Calabi-Yau threefolds and their geometric origin. Now, modular can mean many things in the context of Calabi-Yau geometry. I've had discussions with Noriko Yui over the years as to various interpretations. I do not mean modular Galois representations, although that's fun too. Here we're talking about modular properties of generating functions for enumerative invariants of the Calabi-Yaus. Okay, so that's what we're talking about. And geometric origin, well, quite often you can prove modularity of such generating functions, but you don't necessarily understand how the geometry of the Calabi-Yaus feeds into the structure of modular forms. And that's what we're after. Okay, so for Calabi-Yau manifolds, here we mean a Kaehler manifold, vanishing first term class, maximal holonomy. We probably want some other conditions in there, but we definitely want to exclude abelian varieties just because we're focusing on K3 surfaces in dimension 2 and Calabi-Yau manifolds, traditional sense, in higher dimensions. We may want finite fundamental group instead of trivial fundamental group, but that's another issue. What's striking about Calabi-Yaus is that whereas in dimension 1, when we're talking about elliptic curves, it's just the usual one parameter family of elliptic curves, and you can decorate them up with lots of nice structure and consider modular families and what have you. In dimension 2, you only have K3 surfaces, but there's a lot of room in studying K3 surfaces to stratify the moduli problem with additional structure. Okay, so in the context of elliptic curves, pretty much all you could do would be marking torsion and things like that, level structure. In the context of K3s, what you want to do is just determine which pieces of the K3 lattice. So the K3 lattice is 3 copies of this lattice H, which is also called U. It's U. 1, 0, 1, 1, 0. So this is even hyperbolic lattice. Ring 2, plus 2 copies of the negative definite D8 lattice. Okay. And the Hodge diamond for the K3, 1, 0, 0, 1, 1, 0, 0, 1. And when we talk about stratifying a K3 moduli problem, it's through a process known as lattice polarization. And what you're doing, you're saying that a certain piece of this lattice inside the 1, 1 part, you want to come from algebraic curves. That's basically what the condition is. And that turns your moduli problem, different moduli problem with fewer parameters. Having said that, in the context of K3 surfaces, we have a very satisfying situation analogous to elliptic curves in that our period mapping is surjective onto the period domain, and we have a global Torelli theorem. So if you know the periods for a K3 surface, which is just a list of complex numbers lined up with some kind of marking on this lattice, you know the K3 up to isomorphism. Boom, end of story. Now, making that effective is a whole other matter. And some portion of my research has been dedicated to that, especially my early work with Klinger. But all bets are off when you go to dimension 3 and higher. Okay, so even if you take a very simple Calabi-Yau manifold, and the Calabi-Yau threefolds are going to have Hodge diamonds like this, let's say 2, 2, 0, 1, 1, 1, 2, 1, 0, 0, H1, 1, oops. 0 is right. 1, 2, 3, 2, 3, 4, 1, 2, that's right. Okay, 0, H1, 1, 0, 0, 0, 1. Okay, so this is a Hodge diamond for a prototypical Calabi-Yau threefold. This is one for K3. So for a Calabi-Yau threefold, even if you're in the special case where you have all ones across the diagonal, so natural number of complex structure moduli is 1, because the H2 1, the H(n-1) for a Calabi-Yau n-fold counts the number of complex structure moduli, or H2 1, which is the hard number of Calabi-Yau. Even if those are small and fixed, don't know if we have only finitely many isomorphism classes of Calabi-Yaus. Okay, that's still open. All right. But if you restrict to H1 1 equal 1, or if you restrict to H2 1 equal 1, there's some hope that one could look for a complete classification, possibly through combining existing constructions. So you might have a first construction, and then a second construction, and then a third construction. And if you look in the intersection of this Venn diagram, then maybe you can saturate and come up with a complete classification. So this is roughly, the idea that we would have. Maybe it stabilizes. Okay. What are some standard constructions of Calabi-Yaus? Well, one is as hypersurfaces or complete intersections in toric varieties. You might say, hey, can we do this game and get a real picture of Calabi-Yau geometry? Well, in dimension 2, let's be careful, d equal 2 there is d equal 2 for the toric variety, and we're considering hypersurfaces. Then reflexive polygons, well, there's only 16. Okay, and every one of those corresponds then to sort of a toric Delpizzo surface whose anticanonical is an elliptic curve, and we have families of elliptic curves, so that's a nice construction. You go up to dimension 3, now you have three-dimensional reflexive polytopes. You can look at these and rotate them and play with them in Sage anytime you want, because my former student Andre Novoselsel coded all that up as his first PhD project. And there, in the case of d equal 3, you get 4,319. It's a really sizable number. The anticanonical hypersurfaces there are K3s, and their Picard rank ranges through a wide range of possibilities. For d equal 4, well, you can't visualize the polytopes anymore. You have these four-dimensional reflexive polytopes, and now there's over 473 million distinct polytopes, and therefore Gorenstein toric Fano fourfolds. And every single one of them has anticanonical Calabi-Yau threefolds. You then look at the Hodge numbers, you get about 32,000 different Hodge number pairs, because the only Hodge numbers you care about here are H21 and H11, because H21 is equal to H12 and H11 is equal to H22. D bigger than or equal to 5, we don't have a complete list of reflexive polytopes in dimension 5 and higher. The usual game is you place symmetry constraints or extra conditions on the polytopes, and then you can get a partial classification. Examples at least. Another approach, the early approach in complete intersections, was to consider complete intersections of Calabi-Yaus and products of projective spaces. And we'll see some of that later today. In the old days, and you can see it's the late 80s, okay, these are groups of physicists working hard to come up with examples of the Calabi-Yau that they think is the Calabi-Yau or hope is the Calabi-Yau sought after to make string theory the theory of quantum gravity. This is back in the early days of string theory. People were very optimistic about maybe there being one Calabi-Yau that would do it all. They were interested in generating large numbers of these complete intersection Calabi-Yaus and products of projective spaces. And in the case of Calabi-Yau threefolds, they were able to get 7,890, which is the only ones they were able to get in that construction. You could try non-complete intersections. No reason not to. These are much harder. And there's a literature, again, led by a sort of resurgence of interest from the string theory community in the past 10 years or so, to study these non-complete intersections or near miss of complete intersection Calabi-Yaus. You could change the ambient space. So instead of the ambient space being a projective space or a weighted projective space or a toric variety, you could make it some other nice card number 1 kind of space. How about a Grossmanian? Okay, so homogeneous complete intersections in Grassmannians. That's a good construction. And it turns out you get 33 Calabi-Yau threefolds that way. By virtue of your being in Grassmannians, most of those cases are not realizable in just complete intersections in toric varieties. Okay. Having said that, the key to many of these constructions is to first do what's called a toric degeneration of your ambient space, and then to work there, sort of pull back your information. Okay, another possibility is to just go radically different. There's a lot of room in hypersurfaces, even quintic hypersurfaces in P4. There's lots and lots of room for exotic hypersurfaces, hypersurface families, where your Calabi-Yaus maybe get interesting singularities, things like that, or have high degrees of symmetry. Okay, these are all interesting possibilities. So there's these Pfaffian and determinantal Calabi-Yau threefolds that were studied way back in the early part of this century, and have been of renewed interest over the years. So I would argue, I think most would agree with me, that what we're seeing is probably just the tip of the iceberg. We really don't have a sense of just how many Calabi-Yaus we're dealing with. Okay, so the perspective on a construction of Calabi-Yaus that I want to emphasize today is the notion of fibration structures on Calabi-Yaus. Okay, so these fibration structures are very familiar in the string theory community because they are a necessary component of many string dualities. Right? You want to do a formulation of F theory. Well, you need an elliptic K3 fibration structure. You want to do a formulation of like heterotic type 2 dualities. Fibration structures in your Calabi-Yaus are a necessary feature. Okay. Now, that led mostly physicists to look for sort of a survey, a statistical analysis of the literature of the existing lists. And so most complete intersection Calabi-Yaus are torus-fibered. Okay, that's can be made precise. Okay. In the case of hypersurfaces, in the toric varieties corresponding to 40 reflexive polytopes, 99, and that's a point, not a comma, but that's because my collaborators are both European, 99.38% of the 4-dimensional reflexive polytopes actually have 2-dimensional reflexive subpolytopes. Okay, and our own Boston-based Waddy Taylor actually spoke in a colloquium, I think, here at CMSA on this result. Now, more mathematically, coming from the math community, you could say, well, wait a minute, how do you know you don't get infinitely many different elliptic fibration structures on Calabi-Yaus? Well, okay, and how do you know that the Calabi-Yaus that are elliptically fibered are bounded? Okay. So the first question is more subtle and not necessarily important for the applications today. Even in the K3 case, it's dependent highly on the Picard rank of the K3 surface and the Picard lattice of the K3. The latter question, though, has been established firmly in the torus case by work of Antonella Grassi and Mark Gross back in the early 90s. There's been various follow-up works using higher technology, as you can see from the list of authors in the 21 paper. But the conclusion is that there's a boundedness result. Okay, very high, complicated, effective bound, but there's a boundedness result on the number of torus-fibered Calabi-Yaus, specifically Calabi-Yau threefolds. In the next line, I mentioned K3 fibrations seem abundant. Okay, that's because there was a paper by Candelis et al., Candelis, Constantine, and Skarki, which basically had a similar title. It was that fibrations are abundant. And what they were doing is they were looking for torically induced fibrations on Calabi-Yau threefold hypersurfaces. So as you can imagine, if you want to find a fibration structure on a hypersurface, the most natural thing is if your ambient space is itself fibered, like toric variety fibered by toric subvarieties in codimension 1 over P1. Oh, take your hypersurface and slice it. That's it. It's as simple as that. So that statement about they seem abundant is based on computations like that. I just got back from a week in Essen, Germany, and at my lecture series, there was also Philip Engel, and Philip Engel told me that he just completed with the co-author the analysis analogous to the analysis of boundedness for torus-fibered Calabi-Yaus, for K3-fibered Calabi-Yaus. And again, there is a boundedness result now. So it's a birational boundedness result for K3-fibered Calabi-Yaus. Okay, so you're not going to get an infinite class of non-isomorphic Calabi-Yaus this way, but it's a useful class. An important point that's relevant for us today is that many non-fibered Calabi-Yaus are actually related to fibrations after a flop, and a flop that you can't see using toric geometry. The general definition of a flop has nothing to do with toric geometry. But if your examples are all torically constructed, the most obvious flops to do are the ones that are compatible with the toric structure. The advantage of the approach we're taking with fibered Calabi-Yaus and a classification result I'm going to talk about is that we have access to more general flops. Okay, so constructing K3-fibered Calabi-Yau threefolds with H2 2. Now, this is a request from physicists. Strictly speaking, what they asked was something a little different. They asked for K3-fibered Calabi-Yau threefolds with H1 2. Okay. There was a certain intuition in the physics literature that sometimes, at least, mirror symmetry acts fiber-wise on fibrations. It's not true in general, okay? But at least a starting point, a place where you could look for the kind of Calabi-Yaus they were interested in would be to look at K3-fibered Calabi-Yau threefolds with H2 2. So this fits in to a more general construction and classification, well, classification and full construction of all K3-fibered Calabi-Yau threefolds whose fiber is a K3 with a very particular polarizing lattice. So here we have 3 copies of H and 2 E8s for the full K3 lattice. The polarizing lattice here is what we call MN. Well, I'm going to call it MM because my physics collaborators have reserved the letter small n for something else. Okay, all my other papers call it MN, except this one. So MM is defined to be H, this thing, sometimes called U, plus E8, plus E8, plus, okay, this is rank 16, 17, 18, it's actually rank 19. These are negative definite. This, of course, has mixed signature, and this is minus 2m, which means it's a single class whose square is minus 2m. It's necessarily an even lattice. Put there. As we'll talk about in a minute, these MM polarized K3s arise very naturally in mirror symmetry. They are precisely the mirrors of 2M polarized K3 surfaces. And the 2M polarized K3 surfaces are the simplest class. So 2 polarized K3s are double covers of P2 branched on a sextant. 4 polarized K3s are quartic hypersurfaces in P3, etc. Okay, this is the way you do it. Eventually, you run out of a realization as, say, a complete intersection in a projective space, and what you're stuck with instead is to have to characterize it indirectly, which you can do because you can characterize the K3s through their periods by global Torelli. So instead, you talk about 2M polarized K3s. Everyone knows what you mean. It's another matter to give an effective construction of the full 19-dimensional moduli space of such K3s. This is the 19-dimensional moduli space. These guys have a 1-dimensional moduli space. And in fact, you can work it out really explicitly. This notational shift from little n to little m has resulted in the extremely strange m sub m sub m to denote the moduli space of MM polarized K3 surfaces. Strictly speaking, that isomorphism between the moduli space and the classical or almost classical x naught of m plus requires a little work. Since the lattice polarization is rank 19 and integrating a 2-0 form over an algebraic curve gives you 0, it's the transcendental lattice, the stuff orthogonal to the algebraic stuff, that gives you non-trivial periods. So that means that for the Picard rank 19 family, you have 3 independent periods. Okay, but you projectivize the period morphism. So in fact, you're mapping to P2, fine. And then you have this very nice result that says that any polarized, for that matter, lattice polarized K3 surface has the property that its periods satisfy a quadric condition. Quadric in P2 is called a conic. So you hit a conic. And then you say, oh, but there's a Griffiths transitivity, transversality and positivity result. The positivity result in Hodge structure tells you that, in fact, you hit the upper half plane realized inside the rational curve, which is the conic. So after going through all that, which can be succinctly represented using representation theory as relating a 3x3 matrix to a 2x2 matrix in a very nice way, the 3x3 matrix having integer entries, the 2x2 matrix having some square roots, gives you this x naught of m plus. Okay, so it's the upper half plane quotiented by gamma naught of m plus. Gamma naught of m is what you think. It's the congruent to m with 0 in the lower left entry. The plus means you have to include the Frickett involution, which is tau goes to -1 over m tau. And if you write that in terms of 2x2 matrices, you get square root of m's. So you're in PSL2R, not PSL2Z. Okay, so you've moved beyond the elliptic case, but you're still dealing with modular curves in the sense of K3. These modular curves are very special. For the m's that we're considering, they're always going to have a 0 as a special point. By special points, what I mean. So when I wrote singular points, I mean regular singular points of a differential equation that governs the periods. But what's really going on is that these are the special points in the sense of 2, 3, and infinity being the special points in the J line. You have orbifold points and you have cusps. You always have a cusp at infinity. You always have order 2 orbifold points at these lambda 1 through lambda r, however many there are. And you have what we call an a orbifold point at lambda equals 0. Why? Because we needed a letter that could represent 2, 3, 4, any counting number but 1, and infinity. So it could be a cusp, might not be. Here is the complete list for all of the possible MNs for which you can fiber a Calabi-Yau threefold with MN polarized K3s. There's a bound. The bound is 11. Okay, and you go through and you have this complete list of possibilities of the orbifold types. And there they are. And there are the specific positions of the lambda 1 through lambda r. Now this is kind of fun. You look at the first one and you see the J line. There's 3 to infinity. And lo and behold, where's the lambda, the extra one that's not 0 or infinity? Oh, it's 1728. Okay, so we're taking the standard 1728 normalization. Here we could have divided by 1728 and made it 0, 1, or infinity. You can do that, in fact, for any of the first 4. And the first 4 are beautiful. They're hypergeometric in some sense. If you look at the underlying square root of the Picard-Fuchs equation for this family of K3s, it will be of hypergeometric, Gauss hypergeometric type. It's a very clean kind of story, you can tell. But it's important to note that the classification we're talking about doesn't stop with hypergeometric things. It keeps going. It keeps going to saturate what's possible from geometry. And transcendental geometry, because that's what's governing this story. And you see you have many more possibilities. Sometimes you have 2 cusps, like in the 4 cases, but more generally, sometimes you have a whole bunch of 2s, these things happen. Okay. What is key here is that we prove a result, which is that the deformation class, the complex structure deformation class of the Calabi-Yau threefold is entirely determined by the ramification profile of this map lambda, called the generalized functional invariant, from the base P1 of our fibration to this crazy moduli space MMM. Okay, remember the moduli space, the modular curve of the rank 19 MM polarized K3 surfaces. So we think of this as the direct analog of the classical functional invariant of Kaehler. Kaehler says you have an elliptic surface, you have a map, say it's over P1. You have a map from that base P1, which takes you to the tau for each fiber elliptic curve over a point, and then sends you down to the J line by quotienting PSL2Z action on tau. In other words, the composition gives you a map from the base P1 to the modular curve, which is the J line, which is also a P1. But of course, it's a P1 with extra structure. It has the markings of the 2, the 3, and the infinity. So the local system that lives on that J line, which remembers its meaning as a modular curve, allows you to reproduce the structure. So classical fact, the result of Kaehler, allows you to reproduce the elliptic surface up to isomorphism. Okay? And you get this from his functional invariant, which is the rational map, and his homological invariant, which remembers that extra integral structure in monogram. So we have the same result here. It turns out the homological invariant, which we'll mention later, is only necessary in the case where M is 1. So what do we do to analyze the ramification profile? Well, we consider this morphism from P1 to MMM. We need to record the information about the ramification. So what we do is ramification over the special points is what really matters for us. And so we need a recipe for it. So for example, on the right, you see if we have a map of degree 3, so those are the 3 sheets right over the base. If there's no ramification, that would be 1, 1, 1 type, okay? On the right, well, we have 2 sheets coming together, that's a 2, but we still have a 1 down below, that's 2, 1 type. So we record the information of this ramification profile over the point at infinity, which is always a cusp, and that A orbifold point at 0. And it turns out that that's the only ones that matter for our analysis, because we're going to assume no ramification over the 2 orbifold points, which then corresponds to a generic choice of complex structure in the moduli space we're building. What's beautiful about this is you can just use your old Riemann-Hurwitz formula, and the Hurwitz formula implies that the excess ramification of this map, the ramification that does not take place over the marked points, and by assumption over 0 and infinity, is a number. There's a number of them, okay? And it's K plus L minus 2 generic points. And that's just an easy application of the Riemann-Hurwitz formula. And that's related then to the number of moduli you're getting for the resulting Calabi-Yau threefold fibered by K3s. Okay. For the purposes of this application, we want to specialize further because my physics collaborators wanted H11 equal to Calabi-Yaus on the mirror side. So we want H21 equal to Calabi-Yau threefolds on this side. And for that, you just specialize my construction with Novoselicev and Harder and Thompson to that case. And what you get is that the rational function, right? Here the Y is the base parameter on P1, the base of the fibration, and Z1 and Z2 are deformation parameters. The rational function takes this universal form, where I and J are simply the ramification profile data that we need for the splitting. Yeah, there we go. So the possible IJ partitions, as M runs through these different possibilities, range from just 1, 1 for a degree 2 partition, all the way up to much more complicated partitions. We have, 8 sheets, we have a 4, 4, for example. So the data we want to record somehow is the data I, well, M, of course, I, J, and then S, where S runs from 0 to I minus J. Okay. And with that data, and you see the S showing up in the denominator as the power of S. So with that data alone, if we just pull back, and I put quotes around modular family because we're dealing with a coarse moduli space, not a fine moduli space, you have to be a little cautious, but you pull back a family with the right properties over the modular curve, and you do a crescent resolution after pulling back, you construct all smooth MM polarized K3-fibered Calabi-Yau threefolds. In this case, they are all smooth for these values. We'll denote them Y, M comma S bracket IJ, and they're all going to have H21 equal 2. Okay, and notice my M can change. I'm not stuck with using mirrors of coordinate K3s. That would be M equal 2. I can do M up to 11. But let's do an M equal 2 example. Keep things simple. The orbifold type for M sub 2, right, it's still one of these nice hypergeometric types. I have 4, 2, and infinity as my orbifold types for points. My lambda value, there's just one of them, lambda 1, happens to be at the value 256. That's the analog of the 1728 that we had in the M equal 1 case. You can see the ramification. I mean, we've done some tracing of real loci to draw this graph, so it's not even as crazy as schematic as you might think. But over the cusp, we have 1, 2. Over the 4 orbifold, we have 2, 1. And over the 4 orbifold and the 2 orbifold at 256, we have no ramification. The good news from the standpoint of calculation, of computation, and of feeding information into existing theory, is that we really understand periods well for polarized K3s. They're somehow descendant from what we know about elliptic curves. In a very rigorous way, I could say that an polarized K3 surface is Hodge theoretically indistinguishable from a product of two elliptic curves linked by a cyclic n-isogeny. So the periods there we really understand well. Moreover, you can build periods of the 3-0 form on the Calabi-Yau threefold from the data of the generalized functional invariant map and the periods of the K3 fibers. And this is exactly how you do it. Set it up as this integral. Remember, y is the base, so this is integrating dy over y, and I'm using the data of my generalized functional invariant map, and I'm feeding in the generalized functional invariant map into the regular, the holomorphic period of my polarized K3, which I already knew. Right? This whole thing is annihilated by a pair of operators. This would be the Picard-Fuchs system for this. The first one I wrote down. I don't think I'm going to write down the third one, degree 3 one. But theta here is theta I would be zi ddzi, sort of the standard hypergeometric style notation. And it's very simply written down in terms of the ij. Moreover, and this is again the kind of thing physicists are always looking for, physicists, when they see a Picard-Fuchs equation, a Picard-Fuchs system, want to find a point of maximal unipotent monodromy. Okay, and in this coordinatization, it turns out to literally just be z1 equals z2 equals 0. So why do they want that? Because then from first principles in physics, they know that there's going to be a mirror construction, and that to them, the existence is not in question. There will exist. They don't know how to construct it necessarily, but there will exist. There should be a mirror Calabi-Yau threefold with the H11 then flipped. Okay. In detail, we can now map out the moduli space. We have our H21 equal 1 Calabi-Yau threefolds Y. We have the deformation parameters Z1 and Z2, and we can just map out this moduli space. So the first thing you do is you look at the discriminant, and the discriminant actually factors. Well, each component of the discriminant must have an interpretation in terms of our generalized functional invariant rational function. And it does. Delta 1 equals 0 says that the excess ramification point, there was only one extra ramification point not pinned down in this example, collides with one of the two orbifold points. In this case, it's only one. The delta 2 equals 0, right? Turns out to just be the condition that Z2 is 1. And that corresponds to the excess ramification point colliding with the fiber at 0. Equals 0. So in this example, the delta 1 is very, it's not too bad. The delta 2, of course, is just 1 minus Z2. And you map out the moduli space. This is done with like a minus log coordinates. So the point 0, 0 is in the far upper right. So that first quadrant is where the Calabi-Yau we were talking about is going to be. Now, the other really cool thing you can do is you can take limits. So we talked about the maximum unipotent monodromy point that's easy to read off. We can also take limits. You can take the limit as Z2 goes to 0, keeping Z1 finite. Okay, great. What does that do? Well, there's our generic ramification profile. And what it does is collide those. Okay. If you further impose that Z1 goes to 0, you again get maximum unipotent monodromy of periods, but in a different phase. Okay. So here you're getting your X21 the 2-1 ramification profile. And here you get what's called a Tyurin degeneration. Okay, so this is now sending Z2 to 0, keeping Z1 finite. Tyurin degeneration is something that we certainly talked about in this seminar before. We ran a whole workshop, which I guess you weren't able to attend because you were at the IAS, right? But the Tyurin degeneration then consists of your Calabi-Yau threefold splitting into two components, quasi-Fano components, each intersecting on a smooth anticanonical K3. what's the realization of that? Well, you can literally see in the generalized functional invariant the two components. Okay, the portion there corresponds to the upper half of this ramification profile graph, and that highlighted in blue corresponds to the lower half of the graph. And where do they intersect? At the point in the middle, and the point in the middle is exactly our polarized K3 surface. Where does it happen? What's the lambda value? It happens at 1 over z1 times I plus j to the I plus j over I to the I times j to the j. Okay, a very hypergeometric sounding point. When you feed this in, though, to the DHT mirror correspondence, well, the DHT mirror correspondence is saying that codimension 1 Calabi-Yau fibrations are mirror to Tyurin degenerations. Well, we just found the Tyurin degeneration among polarized K3-fibered Calabi-Yau threefolds, which means on the mirror Calabi-Yau, the thing we were calling X, we must have a K3 fibration. And the K3 fibration must be 2M polarized K3s, because those are the mirrors of polarized K3s. And that's exactly what we observed. Now, you could also take the limit as Z2 goes to infinity, keeping Z1, Z2 to the J finite. And then you observe that there's an involution that relates two different of our Calabi-Yaus constructed using these fibrations. And what it's doing is it corresponds to a flop transition between the mirrors on the other side. So this is something that we can observe on the level of the fibrations, and we can interpret it as a flop transition on the level of the mirror Calabi-Yaus. So this is the kind of structure of the moduli space we get. There's no reason to stop with m equal 2. You can do the analysis, say, for m equal 5, get a more complicated picture, more complicated transitions, and the same analysis applies. Okay, so the point there is that it's relatively easy to map out this two-dimensional moduli space in a very complete way. For constructing the mirrors, we could use the DHT conjecture. In fact, we can use an older result of Lee, one of Igor Lobachev's students, who studied the Calabi-Yau smoothings, a la Namakawa and Kalamata, of Tyurin generations into the smooth Calabi-Yau regime and computed Hodge numbers. The workhorse there is Kalamata-Namakawa smoothing result. But let's go a bit differently, because remember, we're working with physicists, and physicists love the examples they've been using for 30 years. And so the first thing that they want to know, are any of these the same? Okay. So as a warm-up, you can do m equal 2. And constructing the mirrors, well, we have our regular period for our y, MSIJ. Specialized to m equal 2, we get this very nice expression involving the 4d factorial over d factorial to the 4th. And then using either Batyrev-Borisov or Hosono-Clem-Tyson-Yau technology that was developed in the mid-90s by collaborations between mathematicians and physicists, you can identify this particular series as a generalized hypergeometric series that corresponds to the mirror fundamental period of a complete intersection Calabi-Yau in a product of projective spaces. Okay. So once you've done that, you're in great shape. Now you've explicitly realized this is a Batyrev-Borisov mirror. Technically, you have to be a little careful, because you need to worry about the fact that you could have, say, a differential operator, which allows for different structures. But here, since you're working with the fundamental period, and you can just check everything explicitly, you're spot on. And we can do this. We can take, in this case, a generic quartic as the fibers we talked about are going to be 2M polarized on the x side. So that's going to be 4 polarized on the x side. And you work out exactly what the equations are that are cutting out your mirror Calabi-Yau x. And it's given by this generic quartic and a pair of q's. Okay, it's Q1 and Q2. Okay. Now, what's neat about this is you end up with a nodal Calabi-Yau. And a node Calabi-Yau with 2m times I minus s times j plus s isolated nodes. Now, usually when you have isolated nodes on a Calabi-Yau, what you really want to do is get a small projective resolution. The problem with nodes is that you always have choices when you blow them up to construct such a small projective resolution, and you don't know whether the result is actually projective. You can do a small resolution, but it could be non-projective. The usual trick that gets around this is to find a divisor on your space that cuts through the node, blow up the divisor, and then it for free gives you the small projective resolution. Okay. So what you can do here is you can arrange the divisors using the equations we already have to actually pass through all the nodes. And you can do it in more than one way. You can get a small resolution to this x2sij by blowing up along the divisor where p1i and p2i minus s are 0. But you could also blow up by having the divisor p1i and p2j plus s equals 0. Okay. And they're related by a Flop transition. The other thing you can do is you can do a smoothing of your nodal Calabi-Yau. And a smoothing of this nodal Calabi-Yau turns out to be a 4i plus j complete intersection in weighted projective ij1111. So for example, you can get the quintic in this case, when it can be 4. Or you can get this 4-4 complete intersection weighted projective 2-2-1-1-1-1. Just to give you a sense of how the combinatorics all shakes down, you have data like this, so-called L vectors and all that feed into the Batyrev-Borisov mirror symmetry construction, from which you get nice descriptions of the polynomials in affine coordinates, in Laurent polynomials, the big torus. And this is on the y side. And then with variable identification, you can get it down to a clean description of a family of hypersurfaces in the big torus. You could go better than that. You can recognize this cleanly described hypersurface as itself being fibered as a modular family of polarized K3s. So in this case, you can just look it up. You literally plug in and you see, aha, we're getting exactly what in my old paper with Harder, Novoseltsev, and Thompson is the corresponding modular family for M2, I guess, here, polarized K3s. Maybe M4. M4. Okay. So if you consider a family of the x's with a running parameter t, you can degenerate. And this is the mirror degeneration to the fibration on the other side, the polarized fibration. And you get it. To get a Tyurin degeneration, you need a smooth total space for your family. So you have to do some blowing up. What do you blow up? Oh, you blow up along exactly the vanishing loci we talked about before with that Flop transition interpretation on the x side. Okay? So this is in perfect agreement with the DHT conjecture and can be seen as sort of slightly more refined evidence of it in the context of these toric constructions and vibration constructions. And you can do it both ways, right? So you can blow up along these, and you can blow up along these, okay? And they both. This generalizes to the m equal 1 to 4 case, and in every one of the 1 to 4 case, the ones that smell hypergeometric, you get a connection to toric complete intersections or complete intersections in products of weighted projective space. You always get this picture with a Flop transition relating two small resolutions and a smoothing. And you do them all the ones you can access with those small m values, and you line them up with examples that are already in the literature. And you see certain famous examples that people like. These are complete intersection Calabi-Yaus in that original list of Candelas and Hoops et al. And some other famous examples like Optic and 11222 showing up here. Okay, why is our representation with vibration a better representation than the one that was already there? We would reproduce something that's already there. So why is our picture better? Well, if you go through the detailed analysis of the mirror periods, you discover there's a relationship between the parameters that we have, the z parameters, and these parameters W that are showing up in the other constructions. Our representation gives you this picture of the moduli space with the various phases. You get all three of these phases. The flop is manifest in the construction. And the polarized fibration, polarized fibration, and the generalized functional invariant maps are both manifest in terms of the Batyrev mirror. The traditional hypersurface realization does not see these other sectors. Okay, it does not see these. What it's done is it's collapsed in some sense the component of the moduli space hidden inside the boundary. So it's just not visible. The flop between these two examples, the 2,0 and 2,3 cases for X4,1, it's non-toric from the perspective of this hypersurface construction, the classical one. And the fibration and the generalized functional invariant are not manifest in the construction done this way. Okay, but this was all just the case where we expected a connection to toric geometry. For cases M 5 through 9 and 11, they're not toric. There's no reason to expect a direct toric connection. In fact, you're getting complete intersections of Grassmannians. You're messing around with the tautological bundle or the determinant of the dual tautological bundle. Anyway, there's a way to do these using Grassmannians, okay? And once you've done that, you now get a much broader range of examples, okay? And these are examples that you could not access using the toric methods. So if you take, for instance, n equal 5, that's the smallest non-toric case, you do this fun calculation and you realize that our expansion in terms of Z1 and Z2 is a specialization with two parameters specialized to be one of a calculation that a series that you could set up as a generalized hypergeometric series. Okay, this is not surprising. This phenomenon does happen. It happened way back when I did the work with John Morgan on the 14 integral VHS over the thrice punctured sphere. We had some cases where you could specialize from multi-parameters. Here, what happens is you get the mirror pair of the X and the Y from dual conifold transitions, starting from the 4-parameter family. So we have our nodal degeneration that we talked about earlier, small resolution, but the small resolution here, it's further nodal degeneration. Small resolution here results in H11 equal 4 Calabi-Yaus. The mirror, given by a toric construction, known toric construction, is H21 equal 4. With this period we were talking about with 4 parameters, you specialize Z3 and Z4 to 1, and you recover what we have, which we get via small resolution. Contraction, if you like. But anyway, you do a small resolution of what you get there, and that is our Y, okay, recovering the regular period expression. Again, toric descriptions for all this, just to see it can be done in egregious detail. You feed it into the Batyrev-Borisov mirror construction, you follow your nose, just like we did before, where we ended up with that nice expression for the M4 modular family, and you get a conjecture that this had better be the M5 modular family. And using Eric Pichon-Faribaud's software, Eric defended his thesis last week in Paris, and I was happy to be there and ask him a question. You check that this is actually a modular family for M5. Okay, and this was not a known realization in literature for M5 either. Again, you know, the toric data is all very explicit and easy to work with. In this case, if you want to make a connection to the toric world, the way to do it is you take a toric degeneration of your Grassmannian and a suitable resolution thereof. Your toric ambient space is now this P25 hat cross P1, and the conifold transition between P25 hat cross P1 to the Grassmannian cross P1 is what induces this relationship between the X5 Sij and the X tilde. As a result, we get a very explicit description inside this product space by working in P9 because we're using the Fluker embedding or GR25 in P9. And you work it out and you follow your nose, it's the same thing. You get a small resolution of this hypersurface given in these terms, intersected the Grassmannian sitting in P9. A smooth deformation is this X511, and the Tyurin generation argument, analogous to what happened for n equal 2, again checks the DHT conjecture predictions in this case. Now you might say, well, okay, we have a uniform construction of examples. Shouldn't the invariants that you attach to the Calabi-Yaus be given by formulas using those numbers, the I and the J and the S and whatnot, and the M? And they are, okay? So these are Yukawa coupling computations, the K-I-J-Ks for several of them. The product, the dot of C2 with J1 and J2 is both given there. The H11, of course, is 2 by construction. But what about the H12? Well, you get a beautiful formula. And if you look in the middle there, you see that H12 of FMI and FMJ are showing up, right? And these are, of course, coming from the Tyurin generation pieces. So the FMI and the FMJ are final threefolds of degree M and index I. You can use this also, not just to get these topological invariants, but to calculate Grothe-Marvafa invariants for genus 0, genus 1 completely, and in some cases, genus 2. So the last thing we want to talk about is modularity in the case where S is 0, okay? So if I take S equals 0 and specialize, what's going to happen geometrically? Well, what we're seeing when you take S equals 0 is that the X side gets, as we mentioned before, a 2M quasi-polarized K3 fibration on its own, okay? Because the S equals 0 case is where we identified the Tyurin degeneration on the Y side. And by DHT, the Tyurin generation is mirror to the fibration structure. What this means is that you get a map, you can think of it as analogous to the generalized functional invariant map we were talking about earlier, from the base P1 of your 2M polarized K3-fibered Calabi-Yau X to the moduli space M2M, which I mentioned earlier is 19-dimensional for each M. Okay. So you're not going to have a nice clean description of ramification profiles and whatnot like we talked about before. But what you can do, especially if you use the work of Kudla, Nilsson, and Borchards, and you put it all together in the hands of Malik and Pandarapande, is you get invariants you can compute, the so-called Noether-Lefschetz invariants, where you're basically counting intersections with divisorial enhancement. In this case, it's a divisor in the 19-dimensional moduli space of the 2M polarized K3 surfaces, consisting of K3s with a quasi-polarization that contains a class in pick, which squares to 2H minus 2 and dots with the polarization BD. Okay, so it's that old game when you're playing these moduli invariant games. You want to cook up something which is guaranteed to be finite, countable, and enumerative. Okay, and that's the whole point of the Noether-Lefschetz invariants. Then, of course, you could construct a generating function from Noether-Lefschetz invariants, and it's known to be a vector-valued modular form. It's known how to derive the Grothe-Marvafa invariants from the Noether-Lefschetz invariants in this way. And once you do that, you get explicit modular properties for this topological stream. FG top. Okay, in terms of Yukawa couplings, we can actually do all the same calculations with Yukawa couplings. Now you have, as I said before, completely explicit expressions for all of these. And from these, you can derive these and modular properties of the mirror map for the K3s. You can derive, in general, modular expressions for the vertical parts, the parts that are associated to the K3 fiber of genus 0 and genus 1 topological stream motion. Okay. So what do we know? In general, if we have a 2M quasi-polarized K3-fibered Calabi-Yau threefold, It's known that the A-model topological string for energies have gamma naught of m plus modular properties with respect to complex Kaehler moduli. This is sort of known by physics and established by mathematical means. But it's also known that the gamma naught of m plus modular properties are exactly the properties of the periods of the polarized K3s. And you might think, oh, this is something to do with fiber-wise mirror symmetry, but the answer turns out to be no, because mirror symmetry doesn't in general act fiber-wise. What is the more general story? Well, the more general story is this Tyurin degeneration picture. So the limit as Z2 goes to 0, Z1 goes finite, for example, in this M2 case, was mirror dual to the large base limit of the K3 fibration on the X side. And gate is our Tyurin degeneration, whose central point was our K3 of polarized type. So the modular properties of the A-model free energies on Xij M naught are a consequence of the DHT mirror conjecture and the modularity properties of polarized K3s. So the punchline is this claim: modular properties of A-model amplitudes on fibered Calabi-Yau's X are associated to modularity of periods of the central fiber in the dual Tyurin degeneration. And we expect this is a much more general phenomenon as sort of a consequence of DHT, and are in the process of exploring it. Thank you.
Thank you, speaker. Do you have any question? Oh, okay, we have a question from Zoom. Yeah.
Is there a question or a clapping?
Oh, okay. Okay.
Thanks, Arjun.
Just any question from Zoom?
Well, let me just point out something very fun. So I mentioned that I was in Essen last week giving a series of lectures, and then on the way back, I stopped in Paris to attend Eric Pichon-Faribault's thesis defense in Saclay. And on the left here, you see the picture of the poster from our CMSA workshop in June. That was an image that was generated using artificial intelligence by my wife for my webpage. And I got a few weeks back an email from La Recherche to my CMSA email saying, hey, could we use your image? And I had to think about it, right? Because that image is not a Calabi-Yau. That image was generated by us saying, hey, we would like a black background. We would like it to have rainbow colors. We'd like it to look like a Calabi-Yau shape, but more singular, more complicated. I think we said more complicated. It doesn't know what singular is. And it did it. It came up with this beautiful image. But then I had another problem. Once we decided, yeah, we'll give it to them for free. The next problem was they asked for higher resolution. And we thought, oh, all we have is what the AI gave us. We don't have any high resolution. Then we realized you can pay $10 and buy another AI program and ask it to give high resolution. So I know we have a theme going at CMSA this semester on artificial intelligence and machine learning and all. This is nothing as deep as that, but it has produced a cover of a popular French science magazine. So I put that on the shelf of publications upstairs. I think the cover counts.